Let's look at physical properties of organic compounds. If we talk of physical properties, we most of the time mean boiling and melting point. So let's see what factors affect the boiling and melting points of organic substances. Mostly it is the intermolecular forces that would be strong or weak, that have to be overcome with energy required to do so, that will increase boiling point or decrease boiling point if you compare organic compounds' boiling points. So first, let's just see what boiling and melting is. Boiling point is, of course, the temperature where the vapor pressure of a substance equals the atmospheric pressure. So if you just look at this picture here, this substance will start boiling in this Erlenmeyer flask if the upward force equals the downward force of the atmosphere, right? And so we say it is the temperature at which the vapor pressure will equal the atmospheric pressure. The stronger the intermolecular forces, the higher the boiling point. Same with melting point. What is vapor pressure? Well, that is the pressure exerted by a vapor at equilibrium with its liquid in a closed system. More volatile substances, more volatile materials, meaning they evaporate faster, they have got a very high vapor pressure, but it means that their boiling point is relatively low. So they boil fast. They don't need a lot of heat to start boiling. They can start boiling even at room temperature. And so the stronger the intermolecular forces, the lower the vapor pressure. Okay, so let us have a look at just some examples. If you look at the boiling points of alkanes, we can look at methane, propane, pentane, and heptane. Of course, they all have single bonds between the carbons in each case, right? But the number of carbons increase. What do you see about the trend in their molar masses? Well, that is increasing because you add more and more carbons onto the chain and therefore also more hydrogens. What happens with the boiling points? If you increase the molar mass, you also increase boiling point if you increase the molar mass, right? And so you might think, well, in any case, if you have a molecule that has a greater molar mass than another molecule, it will require more energy to break these molecules apart from each other or to overcome the intermolecular forces between them. And so the boiling point will increase, but not so fast. We have to look at some other trends as well and some other data as well. The thing is this. Okay, so now here, there's again a pattern of boiling points. If we look at equivalent molar masses, you look at equivalent molecules, but they are not the same substance, the same molecular substance. But in each case, they are isomers of each other, right? Here you've got two branch chains, one branch chain, no branch chains, this is a straight chain. And here you've got two branch chains, but it's more of a spherical molecule, right? So you can't say because the molar masses increase, the boiling point seems to increase, or because there is no correlation there. So what we see here is that if you have a straight chain with a certain number of carbons, in this case 1, 2, 3, 4, 5, 6, this is hexane, but a straight chain hexane, then the boiling point is 69 degrees Celsius. If you just take one of these, you take maybe the end carbon with its 3 hydrogens off and you make it a substituent onto that chain, all of a sudden the boiling point drops. You take another CH3 and put it as a side chain and the boiling point drops again. And now you make it even more spherical, this molecule, and the boiling point is even lower than before. So it seems as you go from a straight chain to something that is more branched, that the boiling point is affected. Let's see how that works. So there are basically three factors that affect boiling point: intermolecular forces, the number of carbons in the chain, which will affect the number of electrons in the molecule, and the branching of the organic chain. That affects boiling point. Now, this is a relevant strength of the four intermolecular forces that you know by now. Ionic has greater intermolecular forces than a molecule with hydrogen bonding between molecules. That again is stronger than two dipole molecules that are intermolecularly attracted to each other. And then that is even a stronger intermolecular force, the dipole forces, stronger than London dispersion forces. Normally, this is your weakest type of intermolecular force that exists between non-polar molecules, for example, between CH4 molecules, right? If you have lots and lots of methane gas in a container, there's many of these CH4 molecules, and there are forces that act between the molecules. We call those intermolecular forces. And these forces are very, very weak. They are weak London dispersion forces, right? Because these are non-polar molecules. And of course, you should know how those intermolecular forces are set up. But normally, the stronger the intermolecular forces between molecules, the higher the boiling point. You need to remember this and understand this, that if a substance boils, the intra-atomic bonds do not break. Only the intermolecular forces are overcome. And so in order to overcome those intermolecular forces between molecules, energy is required to overcome those forces. And that amount of energy required gives you a certain temperature at which that substance will then boil, and that's the boiling point. So the stronger the intermolecular forces, the greater the boiling point, or the higher the boiling point. If we look at number of carbons on the chain, that will increase the number of electrons within that molecule. You will have therefore a greater electron cloud density and more distortion of the electrons constantly moving and swishing around in that molecule. The more electrons you have, the more of a denser electron cloud you have. And all of the swishing can cause distortion, right? So the greater the molecule, the larger this electron cloud that can be distorted, and the greater this distortion, that at some point in that molecule will result in more electrons on the one side and less electrons on the other side of this electron cloud. We call this distortion. And now just for a moment, you can get what we call a momentary dipole setup, because this will be your partly negative and this will be your partly positive side of the molecule. And excess, more electrons in a region makes it more negative. Less electrons compared to this side will make it more positive. And so you have two poles. This is what we call momentary dipoles that are then created in a molecule that would normally be non-polar, like methane. The electrons are constantly moving, swishing around, and as we explained, the electron cloud density can become distorted, where at any point in time, the electrons spend more time on the one side than on the other side of the molecule, creating these momentary dipoles. And these momentary dipoles will then induce momentary dipoles in neighboring molecules. So in a neighboring molecule, a cloud will be electron cloud that is distorted, will be set up just in the opposite way to what we have set up here. And so this will be your partly positive, and this will be your partly negative side. This will be your partly positive and partly negative side. And as you know from electrostatics, opposite charges will attract. So there will be attraction between these molecules, not within the molecule, but between the molecules. Just for a moment, which we call London forces, the London dispersion forces. It's very weak, but the more of these electrons you have, the greater the magnitude of these London forces, and therefore you require more energy to overcome these greater magnitude of London dispersion forces, and therefore the boiling point will increase. Take note, saying that the molar mass of substance is more than that of another, and therefore its boiling point will be higher, will give you 0 in the exam. You must mention about the number of electrons within that molecule that will get distorted and set up the momentary dipoles, which will then lead to stronger London forces between molecules and adjacent molecules, also inducing the momentary dipoles in one another. And therefore more energy is required to overcome those stronger intermolecular forces, and therefore the boiling point is higher. There is a certain sequence in answering any question where you're asked about comparing boiling points. First, you have to identify the type of intermolecular forces that exist between molecules of the 2 different substances you are given. Then you decide which of those 2 substances have stronger intermolecular forces between their molecules. Then you'll have to say more energy is required to overcome, not break, but overcome the stronger intermolecular forces in the substance that you're comparing with that of having weaker intermolecular force. And therefore, that substance you have chosen with the stronger intermolecular forces between molecules will have a higher boiling point than the other substance with weaker intermolecular forces between the molecules. We have looked at branching of the main chain, and we said that, of course, the more branching, the weaker the intermolecular forces will be. Why is that? Because if you have a straight chain organic substance versus one that is very branched, okay, straight chain molecules can pack very closely together, which will pull them in closer together, and you'll get a greater magnitude of intermolecular forces that are stronger, acting over a shorter distance. And so you need more energy to overcome that greater magnitude of more intermolecular forces, because the molecules pack so closely and nicely together. Therefore, you'll have high boiling points with straight chains between straight chain molecules than branched chains. With branched molecules, right, you will have the substituted groups sort of sterically hindering and spatially hindering adjacent molecules to come very close to one another. And therefore, the intermolecular forces between those molecules are not as strong. And so you need less energy to overcome the existing intermolecular forces, and therefore you have lower boiling points, right? More branching, less energy required to overcome the weaker intermolecular forces, and so therefore you have lower boiling point. If we look at alkanes, alkenes, and alkynes, we see something interesting, right? So yet again, if I look at an alkane versus an alkene versus an alkyne, you might first think, oh, let's look at the intramolecular bonds, meaning this sigma bond and the sigma and pi bond and the sigma and 2 pi bonds here, and see how there are more bonds here with alkenes, with alkynes than with these 2, and so the boiling points are higher. No. The boiling point has 0 to do with the intramolecular bonds, the proper bonds. They do not break during boiling. The intermolecular forces between molecules determine boiling point. So why is it, do you think, that if we just compare boiling points of alkenes, alkanes with equivalent alkenes with an equivalent alkyne with each other, that the boiling point is increasing? Well, the reason for this is, as we've already explained, right? If you have a more straight, more linear molecule, the molecules can pack closer together, which will increase the intermolecular forces, and therefore more energy will be required to overcome those stronger intermolecular forces. There will be higher boiling points. The thing is, if you have increasing linear structure, meaning alkanes are not as linear as alkenes, are not as linear as alkynes. Remember, the more pi bonds you add between carbons, so if you go, for example, from alkenes to alkynes, there's more pi bonds between the carbons. You restrict the rotation and the movement of the neighboring, of the carbons involved in that double bond. And so you get more linear molecules, right, that are more restricted to motion and rotation, and maybe looking like that instead of looking like this, right? So you will have that the molecules are more linear in structure. They can close more, pack more closely with adjacent molecules. And therefore, the magnitude of the attractive intermolecular forces increase between the molecules. More energy is required to overcome, not break, the stronger intermolecular forces. And therefore, you have higher boiling points for the alkynes, lower boiling points for the alkenes, and the lowest boiling points for the alkanes in comparison with equivalent molecules that just have more and more or less and less double or triple bonds in the molecule.